So today's going to be a really hard lecture. We're covering deriving some important results, namely the electric field near charged disks, rings, and plates, like planes of charge. The derivations themselves are really hard, so a natural question is, why are we doing them at all? And it's because they're extremely important concepts in the derivations that you'll need to apply, if not in this class, very soon, so it's good to see them now. However, at the end, we're going to get results for the electric fields near those objects, and you're never going to have to re-derive them. So you don't need to feel lost or dumb because you don't follow this, because in reality, a lot of you are going to have trouble following this. But as long as you get the main concepts, that is OK, and you can just use the results. I will have a summary slide where all the results are collected. OK, also, our textbook goes against the grain and uses eta for surface charge density, like if you smear out some coulombs of charge over a piece of paper. The rest of the world uses sigma, and I've been using sigma my whole life, so I'm probably going to accidentally write sigma. Our textbook uses eta, so they're the same thing. Just be aware of that. OK. Also, one more thing is I forgot to remark in one of the previous classes that objects don't feel force from their own electric field. So they only experience the electric field due to other objects pushing them around. They don't feel, at least for point charges, they don't feel the electric field that they are creating. Again, that's just an odd end I think I forgot to remark last time. Obviously, extended objects, they will feel their own electric field, but only in terms of trying to explode. So we're always going to ignore this. OK, so as promised, here I've included some summary slides. We're going to today derive the electric field near a line of charge, near a ring of charge, near a solid disk of charge, and near a spherical shell of charge rather than a point charge. Okay, this is just results for later. All right, first thing we're going to need for these derivations is something called charge density. So charge density is what happens when, rather than all the charge being located at a specific point, like for a proton, the charge is spread out over the surface of an object. Just as an example, if you spread out 20 coulombs of charge, if you distribute it over a stick that is 2 meters long in length, the charge density of the stick, it's the total charge over the length of the stick, which is going to be 20 over 2, so 10 coulombs per meter. And people like to call this lambda, the charge per unit length of a line. There's a similar concept if you have, let's say, a square piece of paper that's 2 meters by 2 meters large, and you spread out 20 coulombs over the surface of the piece of paper. Some people, by the way, I should mention, people like to call this the linear charge density, because obviously it's along a line, so the linear charge density. Here we have the area charge density, or the surface charge density. You take the charge over the area, which in this case would be 20 coulombs divided by 4 meters squared, to get 5 coulombs per meter squared. And again, people call this sigma or eta, depending on if you use our textbook, which uses eta, or sigma, which is the rest of the world. OK, so people like to condense these equations. For some reason, people chose to use different letters when it's an area versus a length. And there's another one for volume. If you have 20 coulombs distributed over a certain amount of volume, people like to call that letter rho. That's the volume charge density. And of course, you can multiply through these formulas to get the expression for the total charge on an object in terms of its charge density. So again, I'm just multiplying over by the denominator. Oops. Okay, so these, next slide has these all tabulated, by the way. Oops. Let me just check one thing here. Okay, now a natural question is, so this works if lambda is a constant number, like 4 coulombs per meter over the entire length of the stick. But sometimes the charge is not evenly distributed across an object. Maybe there's more charge located on the right end than the left end. So as usual, going back to the very first day of class where I told you that this formula work equals force times distance only works if force is a constant over the whole distance. And if it's not, you have to integrate force d distance. Here, if you want the total charge on an object, let's say a line, which doesn't have a constant lambda, you need to integrate lambda dx. As an example, maybe lambda is the function 3x. So at x equals 0, the rod has a charge density of 0. And all the way at the right edge of the rod has a charge density of 6. The question would be, compute the total charge on that rod. And you're going to do that by doing an integral. And you're going to do an integral right now. So talk amongst yourselves. I'll give you guys about 2 minutes for this one. I chose the function 1 over x squared for a good reason, which I'll tell you later. Who needs a little bit more time on this? Raise your hand if you need a little more time. right. 3, 2, 1, show me. Okay, perfect. Probably 95% of people got B, which is the right answer. I'll show you how to do it real quick. All right, so the total charge, as I told you, when lambda is constant, you just multiply lambda times the amount of distance you go. But if it's not constant, you integrate lambda d distance, because lambda is changing over the distance. All right, so I'm integrating 3 over x squared from 1 to 3. Antiderivative of 1 over x squared is minus 1 over x. So this is minus 3 over x. Right? If you take the derivative of 1 over x, you get minus 1 over x squared. Evaluated at 3 compared to 1. So we have negative 3 over 3 minus negative 3 over 1, which is minus 1 minus negative 3, which gives us 2 coulombs of charge total. Good. I gave you the integral of 1 over x squared because we're going to be using it all day, because electric field, it goes as 1 over r squared, and we're going to be integrating that. Yeah, I heard some O's, yes. 1 over x squared is really crucial. Okay, and here's a page of reference formulas in case you ever need them. So here on the left is how you get the charge densities from the total charge. Middle is how you get the total charge from the charge densities. That's just multiplying those over. And when the charge densities aren't perfectly constant, this is how you get the total charge by integrating. Okay, this is just a reference sheet. Don't copy this down. It's available online. Okay, so now we start the main event. I'll give you guys a little bit of time. You don't need to write like all these words down. But a quick reminder, so our whole goal is we're going to find the electric field near a large object like a disk. It's not a point charge. And our formula for electric field that we know so far, kq over r squared, that's only true for point charges or equivalently really, really tiny pieces of the whole object. Okay? So we're not able to use this formula unless we're talking about a point charge. We're going to learn different formulas. For example, near a disk, it's like E is kq over square root r plus the radius squared, or something weird like that. We're going to learn different formulas for the electric field near those objects. Okay, I also want to advise you guys, there's a lot of symbols involved, like the radius of the disk might be capital R, and the actual variable distance might be lowercase r. Some books use z, some books use x. Some books use x for radius. There's just endless confusion, so always just look at a diagram and make sure you have the right variable in mind. Okay, so as you might guess from this statement right here, we're going to be using this tactic of taking an object. Our first example on the next slide will be a ring. And we're going to break it up into little pieces of size dq, that much charge. So we're going to break into little chunks of little bits of charge. And we're going to add up the electric fields due to all of those little chunks. In order to do that, we're going to meet this weird object dq, which I want you to, every time you see it, just recognize a little bit of charge is either going to be lambda times however much length you were considering, if you're in the 1D case. If you're in the surface case, it's going to be the surface charge density times however much area that chunk occupies. Or in the volume case, it's going to be the volume charge density times however much volume that little chunk that you're inspecting occupies. Okay, so we're going to make this replacement all the time in formulas. And specifically, we're going to make the replacement that the electric field associated to this little bit of charge is Coulomb's constant times dq over r squared. So we're going to use this as, we're going to use this as a building block or it's the electric field associated with each building block and then we're going to add them up to get the total E field. And again, when I say add up, since we're dealing with really tiny chunks, instead of summing, we're going to integrate. I have to wear this glove, otherwise my palm triggers my pen. Okay, so the ring in some ways is the easiest example, but also it's going to be the hardest because you're learning all the new techniques. So again, just try and hold on here. Ask questions if you need. So we're going to be concerned about this situation. We have a thin line of charge of density lambda. Okay, so the charge is spread out over the ring. And we're going to be concerned, what's the electric field a distance z from the center of the ring? Okay, so we're going to ask the question, how big is the electric field arrow at this point right here? Okay, first step is we're going to just sort of imagine the direction of the electric field due to each little element. So this element up here, up top, is going to contribute an electric field arrow pointing in this direction. You assume it has positive charge for now. And also I should mention the hoop has radius A. Okay, so that bit up there is going to contribute that electric field arrow. And this bit down bottom, in some sense, it's like the partner of that guy up top, the one across the diameter. He's going to contribute this electric field arrow. And we're just going to go around the whole circle and add up all the arrows that are generated. However, you now notice that these two partners, they actually cancel each other's vertical components. Right? This guy has an up arrow component, and this guy has a down arrow component. So when we add up all the little arrows together, each arrow and its partner, their vertical components are going to cancel. So therefore, we know just by looking at the problem and drawing the directions carefully, the result is only going to be pointing in the, we'll call that the z direction. The final electric field arrow will only have a rightwards component. And again, we got that just by looking at the disk, drawing the arrows, and investigating what we think the picture will look like. So the symmetry tells us the actual E field will only have a z component. And again, z points to the right in this problem. So whenever we're doing our integrals and things, we're adding up all these vectors. All we care about will be the z components and adding them up, because we know all the other components are going to add to 0. Okay, next, we want to write out the actual equation for how big these arrows are. Before we would write E equals KQ over separation squared. Now we're going to write K dQ over separation squared. And again, R here is not the radius of the ring. It's the distance from the dot to the point that you are considering creating the charge, or sorry, creating the electric field. And as I told you, whenever you see dq, just instantly replace it with lambda times dx. Or some people write it lambda dl, which I'm going to do here, because it's a curved line. Okay, now I told you we're going to add up all of these components only. We're only going to care about the horizontal components. So instead of adding up the total size of all the E field arrows, because we aren't using all their components, we're only going to consider this horizontal part of the arrow, and we're going to add up all the horizontal parts of the arrows together. So instead of adding up k lambda dl over r squared, which is the total size of the arrow, we're only going to add up this times cosine theta. Right? Because we don't care about the vertical parts. They're going to cancel out. We're only adding up the horizontal part. And again, this is the electric field due to this little chunk up here, dl. OK, now all we need to do is rewrite r, which again is the distance from the dot to the little chunk, and cosine theta in terms of a and z. So r is the distance from the creating element to the observation point. So r is square root of a squared plus z squared. And theta, here's theta. So cosine of theta is adjacent over hypotenuse. Okay, and I'm just going to make these replacements in that formula now. Okay. I'll let you guys finish writing that. I know it's a mouthful. Okay, and now all I have to do is integrate this over all the L's, and then I have my result. Right? If I total up all the little bits of dE, I get the actual amount E coming from all the parts together. Okay, but it turns out that, or I shouldn't say it turns out, in this example, as you go around L, as you go around the ring, A and Z, they don't depend on which L of the ring you're investigating. If there were another L in the problem somewhere, which will happen soon, but don't worry about that yet, everything else is just a constant in this integral. So there's actually no integral to do here. The integral over dl evaluates to the total length of the ring, which is 2 pi a. And then nothing else changes. Okay, and coincidentally, lambda times 2 pi a is the total charge on the ring, right? It's the charge density times the length of the wire. So it's actually the total charge on the ring. So this leads us to our formula that the E off the disk is K Q Z over A squared plus Z squared to the 3/2. Okay, again, that was probably more confusing than it needed to be because it's the very first example, but now you know how it works. Okay, and again, in this case, there was no integral to do because L didn't appear again in the integral. It doesn't even really seem clear how it could, but next example it will. Oh, is everyone good copying that down, the final formula? No? Okay. Keep going. Yes, question? Yes, he asked, is the charge uniformly distributed? And yes, that is an assumption I am making in the problem. Without it, the problem becomes extremely hard to solve. Yes? Oh, so it's sort of just a coincidence that I noticed it. It's because I've done the problem before, obviously. So lambda times the length of the ring should give you the total charge of the ring. And the diameter, or sorry, the circumference of a circle is 2 pi times its radius. Good question. Wait, quiet down everyone, just so I can hear. Speak really loud. Yeah, so let me go on to the next example, and you'll see an example where it does appear, because this one's kind of hard to see how L could even possibly appear again. So we're going to go to the next example. Okay. Next example is going to be a solid disk. Okay, this time, quiet down, quiet down. All right, this time the charge is smeared over a surface. It has a surface charge density, I'm going to call it sigma, otherwise I'm going to forget anyway. Again, we're going to have a radius A, and we're going to be considering the electric field a distance z away from the center of the ring. Okay, we're going to follow pretty much the same procedure as before, except this time we're going to use area for dq instead of length. Okay, just by the symmetry of the problem, again, every point and its partner opposite it on the circle, no matter what radius you're at, they're going to cancel each other's vertical components, so we're only going to be left with a rightwards arrow once more. So whenever we're doing our manipulations, we're only going to care about adding up the horizontal components of the little DE arrows. Okay. Now, as before, the electric field, due to a little bit of area this time, is going to be k dq over r squared. And like I said, for area, you always just replace dq with sigma dA. Okay. Now, we're considering the contribution from a general square located a distance r. Sorry, I know that's really small. This is a little r right here. A distance r from the center of the dot, or sorry, from the center of the disk. Beforehand, we only had charge lying all the way at the edge, but now you have charge distributed all the way through. So a general element is located at distance r from the center. Okay, now dA, and this is something that you may or may not know yet, but I'll have a reference slide up next to show you how to do it. dA, we're going to use the formula for the area of a circle, which is area equals pi r squared. And we're going to take the, I guess the derivative of this is more like the differential. To rewrite dA is 2 pi r dr. And I should actually, I'm going to convert the denominator to d. Remember, d is the distance between the little dot and the point that you're considering. Okay. Now, just like before, it's our job to, well, okay, I forgot to say, you need to multiply by cosine theta again. Because, again, you're only concerned about the horizontal part of each of these arrows and how those horizontal parts add up. Now it's our job to replace d and cosine theta in terms of little r and z. So as before, d is going to be square root of r squared plus z squared. Before it was square root of a squared plus z squared because everything was located at the outer edge, but now it's not. And cosine theta is going to be cosine theta is going to be z over square root r squared plus z squared. All right, now making these replacements in the expression for dE, you get k sigma 2 pi r dr z from the cosine theta over r squared plus z squared to the 3 halves. And I know I'm going quite fast here. Okay, and now all we have to do is total this up over all the different radii that are involved in the disk, and that'll give us our answer. So the electric field will be, you integrate over radii going from 0 to the maximum radius being the actual radius of the disk. I'm only going to keep the variable of integration in the actual integral, and all the other numbers are going to come out front as constants. Okay. And now you have an ugly integral to do. Okay, again, don't worry if this was a little bit confusing, the process to get to this integral. But the motivation behind it of totaling up the infinitesimal contributions is what I want you to take away. Okay, now, does anyone know how you do this integral off the top of your head? Yes, U sub. I like you said it instantly. So I wanted to give you guys, for your benefit in this class and life, a quick tier list of integration methods. So, or your checklist, I should say. It's sort of a tier list. So, again, it's really a checklist you should be following. All right, first one is you instantly know how to do it, like it's a power rule, or you can just look at it and do it. I'll call that integration by inspection. That doesn't even really count, but all right, the first non-trivial answer is U sub. This covers probably 90% of integrations you'll ever need to do in your life. All right, anybody know what option 3 is? Trig sub, no. Integration by parts, you're close, but it's actually U sub again. And it's the more sneaky variety of U sub, where it doesn't look like a U sub, but you should probably try U sub before moving on. This is especially true if there's denominators involved. The chain rule can make U subs work in really weird ways. Way 4, integration by parts. And then way 5 is going to be trig sub. This is extremely rare. You love trig sub? Yes. Sorry, say one more time. On the technique of U sub, how you do it? Oh, the sneaky U subs? Things like 1 over square root of x squared plus a squared. Maybe things like this, where it just looks impossible. You just try random U subs until it potentially works. Yeah, you'll see them sometime. You'll know when you get hit with one. Okay. I was going to have you do the integral, but I don't have enough time for that. It is a U sub. You've probably done plenty of U subs in your life. So the result for the disk is on one of the prior pages. So I'm just going to leave it there for you. It just depends on the surface strength of the disk and how far away you are from the disk, as well as how big the disk is. Okay. An important case, hold on. An important case is the infinite plane result for the disk. So the result for a disk is that the electric field is the surface charge density over 2 epsilon 0 Remember, epsilon 0 is 1 over 4 pi k Coulomb. So you see, it depends on how far away you are from the disk, that's z, and it depends on the radius of the disk and how charged up the disk is. Okay, an important limiting case is when you get very close to the plane, or you make the disk extremely big. So that is to say that A is much, much greater than Z. The disk is much bigger than you are close to it. The disk is 50 meters big, but you're 2 centimeters away from it. In this case, the second term goes to 0 because A goes to infinity. And you're left with this result. For the electric field, just off of a very, very, very big sheet of charge with charge density, sigma. Okay, the electric field points away from the sheet on both sides. And the size of the electric field arrow is the surface charge density over 2 epsilon 0. And again, you can get this in a couple ways. But one way available to us now is taking the disk and taking one of the variables to be really, really big. This is a formula you'll use quite a lot. One specific example of where you'll use this is in a parallel plate capacitor, which you're going to learn to hate over the course of the course when you use it in circuits. Oh, do you need to finish writing? Yeah. Oops. There you go. Something I'll point out while people are writing, this is independent of how far away you are from the plane, which is bonkers. It doesn't matter if you're right next to the plane or further away or 4 times as far. As long as the plane is extremely big, you don't care. The electric field is the same size all the way through, all the way distances away from it. Epsilon 0 is 1 over 4 pi k. I'll clarify my reason for swapping abruptly to epsilon 0 next lecture when we do Gauss's law. People will swap between them. Okay. A capacitor is a different kind of object that we're going to care about the electric field near. It's going to be when you have a big plate of positive charge density sigma and another big plate of charge density minus sigma. So you have a bunch of positive charges loaded onto one plate and a bunch of negative charges loaded onto the second plate. Okay, now in the region immediately in between the two capacitors, the positively charged plate creates an electric field pointing to the right of size sigma over 2 epsilon 0. And the negative plate creates another electric field also pointing to the right, pulling towards the plate, also of size sigma over 2 epsilon 0. So the two contributions add. To give you the formula for the electric field inside of a parallel plate capacitor, which is just twice the formula for near one infinite plane. Okay, there's no 2 here in the denominator because it's made of 2 plates of oppositely signed charges. Go back, go back. Yeah. This is written down on one of the slides already. You need the diagram, though. That is an important one. Actually, I lied. This isn't written down on the beginning. Good call. All right, good? All right, next case, an infinite line. Okay, this concerns a long line of charge density lambda. And you're concerned about the electric field strength a certain distance r away from the line. Okay, so here's your line of charge, and you're concerned about the electric field a radial distance r away from the line in any direction around it. Now, just by the symmetry of the line, the electric field points radially outwards. Okay, this is kind of hard to draw, but if here you're looking down the tube of the line, the electric field points in a circle away from it, sort of like how a point charge has that sort of spiky ball emanating from it. Okay, and the result, which I'm just going to give you, is that the electric field is the lambda of the line, so how charged the line is, divided by 2 pi epsilon 0 r. And it points radially away. Just notice people like to write 1 over r squared because you write it all the time. This is a 1 over r fall off, not a 1 over r squared fall off as you move away from the line. I was going to do the derivation. You don't need to write this down. The derivation involves trig sub, so it's obscenely difficult. Okay. Everyone good here? All right. This says infinite line continued. I meant to write this should be a spherical shell. Okay, so we're not going to derive this one because it's actually nearly impossible to derive using our current methods. This concerns a hollow shell of charge with total charge q on it. And you can call its radius a if you want. And I'm just going to state the result. The result is that the electric field outside the shell, it's just kq over r squared again, just like it was for a point charge. This is an enormous coincidence. Enormous. If you do the actual calculation, which is done in like electrodynamics, Jackson is a famous book that does it. It's an incredibly difficult, like true vector calculation, no shortcuts, all pain, but it just comes out to the exact point charge result. However, two things. First of all, this is only true outside the shell. Second of all, r is the distance to the center of the shell, not to the surface of the shell. Okay, all the time you're gonna be given the radius of the shell and the distance from the surface, and you're gonna plug in the distance to the surface and you're gonna get it wrong. It's the distance to the center of the shell. The other extremely surprising result is inside the shell, the electric field is 0. There is no electric field at all inside the shell. Even if you get, obviously at the center, there's no electric field, but if you get really close to the edge of the shell, you would expect the electric field might push you backwards because there's a lot of positive charge there. But it turns out it doesn't. There is identically 0 electric field at all places inside the shell. Again, it involves extremely sadistic vector calc. An intuitive way that you can sort of understand what's going on is, yes, as you get very close to the edge, you're getting close to this bit of charge. But at the same time, the charge or the other charges used to have forces that canceled. And as you move away from them towards here, those charges no longer cancel, and they push you back towards the edge. But it's not supposed to be intuitive. This is a very non-intuitive result that the electric field is zero. It's sort of like how in gravity, if you did it in physics 1, when you'd only consider the mass of shells beneath you, not the mass of shells above you when you're doing gravity calculations. Question, yes?
Yeah, I just want to clarify. So when you say that R is the distance to the center of the shell, that's just A in that figure, right?
No, it's the distance at the observation point. So the electric field at a point out here.
Okay.
Yeah, good question. Very good question.